The Big Bang Theory explains the early development of the universe. According to this theory, the universe expanded from an extremely small, hot and dense state called singularity. Since then, it has expanded and become less dense and cooler. The Big Bang is the best model to explain the creation of matter, space and time. 13.7 billion years ago, the theory has several key features and predictions which have been supported by various observations and experiments. Evolution of the Big Bang Theory. The history of Big Bang Theory can be traced back to several key developments in theoretical physics. Einstein's general theory of relativity. 1950. Einstein's theory provided a foundation for understanding the behavior of space and time, which would later be applied to the development of the Big Bang Theory. Carl Schwarzschild's solution. 1960. Schwarzschild found a solution for a point-like mass which describes a non-rotating black hole. Alexander Friedman's solution. 1922. Friedman discovered the solution for an isotropic, same in all directions and homogeneous, same at all locations universe where any and all types of energy including matter and radiation were present. In 1927-1931, Georges Lemaitre, the father of the Big Bang Theory, proposed the concept of an initial point of concentrated mass suggesting the origin of space and time. Formation of the present universe. The Big Bang Theory proposes that the universe begins from an infinitely hot and dense single point known as singularity around 30.7 billion years ago. Singularity refers to a point where the concept of space-time breaks down and the laws of physics do not work. It is a point of infinite density and gravity. The center of black holes and the Big Bang are considered as the point of singularity. Big Bang singularity. This model predicts that the universe began from an extremely dense and massive point where space and time did not exist. Hence, it is also hypothesized as the Big Bang singularity. Planck epoch. Singularity represents the earliest period of the universe known as the Planck epoch. The physical theories of general relativity and quantum mechanics are not applicable before this epoch. Instability. Due to the extreme heat density of matter, the state of the universe was highly unstable. The Big Bang. Cosmic inflation in the first instance for a fraction of a second 10 to 32 seconds about 13.8 billion years ago, called cosmic inflation. The period of rapid expansion is believed to have set the stage for the Big Bang. The explosion. Just after the inflation, the universe entered into a state of explosive expansion. Light and present matter form. The driving energy of the Big Bang was converted to matter and light. The initial cosmic matter evolved into the building blocks of our present reality like atoms, molecules, etc. Fundamental forces. Along with matter and light, other fundamental forces of physics such as strong and weak nuclear forces and electromagnetism came into existence. Evolution of the present universe. With further cooling and expansion, more complex structures like stars, planets and galaxies emerged. This process continues to this day with the universe still expanding and evolving. Evidence supporting Big Bang Theory. The observations supporting the theory and its proposal include the present-day continuous expansion of the universe and the experiment performed through CMBR. The expanding universe. Hubble's observations. Earlier, it was believed that the universe was static. However, in 1924, astronomer Edwin Hubble revolutionized our understanding by measuring distances to remote celestial objects. He revealed galaxies are moving away from each other, and the farther they are, the faster they are receding. Spatial expansion analogy. Hubble used the analogy of dots on an expanding balloon. For example, two dots on a deflated balloon would be very close to each other, but when we inflate the balloon, those dots will move away. If we choose a dot representing a celestial object, all others are moving away, with those farther away receding more rapidly. Hubble's discovery not only demonstrated the universe expansion but also revealed the existence of galaxies beyond our Milky Way. Cosmic Microwave Background Radiation (CMBR). It was discovered by Penzias and Wilson as the leftover heat radiation from the Big Bang. During the Big Bang, the heat and temperature would be extreme, but currently it is a 2.7 Kelvin. This radiation permeates the entire universe. This residual radiation is recognized as evidence of the Big Bang. Temperature variation. Two probe studies were carried out to find the temperature variation as a measure of the density differences in the universe. Evidence against Big Bang Theory. Though experiments support the Big Bang Theory, there are multiple observations which are against its proposal, such as light elements lithium and helium. The Big Bang should produce a specific amount of lithium and a large amount of helium. However, it was observed that older stars have less lithium than predicted, and nearby stars have less helium than expected. Antimatter annihilation. The Big Bang should create equal amounts of matter and antimatter, leading to low matter density, but the matter density is much higher than predicted, suggesting an unknown asymmetry. Surface brightness. As the universe is expanding, it should cause distant objects to appear dimmer. However, the surface brightness remains constant with distance. Cosmic Microwave Background Anomaly (CMB) is a smooth relic of the initial Big Bang radiation. However, the anomalies in CMB are too small to align with predictions. Inflation theory introduces unknown forces to explain discrepancies. Dark matter. The Big Bang requires the existence of dark matter. Multiple lines of evidence, including galaxy motions, dispute dark matter's existence. Each experiment failed to detect dark matter particles. Alternative theories of the universe. While the Big Bang theory is the most widely accepted explanation for the origin and evolution of the universe, there are alternative theories that have been proposed by some theorists. Steady state theory, an early rival to the Big Bang theory, steady state proposes the continuous creation of matter throughout the universe to explain its apparent expansion. However, this theory has been largely discredited due to the discovery of the cosmic microwave background, which provides strong evidence for the beginning of the universe. Causal set theory. Though major theories of the origin of the universe, along with the Big Bang theory, consider space and time as continuous, where two points can be close to each other in space as possible, but the causal set theory reimagines space-time as a series of discrete chunks or space-time atoms. This theory would place a strict limit on how close events can be in space and time, since they cannot be any closer than the size of the atom. Multiverse. The multiverse theory suggests that there are multiple universes or bubbles of universes, each with its own set of physical laws. It follows from the Big Bang theory and inflation theory, which predict the existence of more still inflating space. Some cosmologists propose that our Big Bang might be the rebirth of one single quantum multiverse containing infinitely many different universes all occurring together. In this view, the Big Bang arises from almost nothing and represents a physical universe, however empty. The multiverse theory is not a replacement for the Big Bang theory, but rather an extension of it. It attempts to explain the fine-tuning of the universe and the existence of a set of conditions that leads to the Big Bang.